My name is Marco Gatti. I'm a postdoc from the University of Pennsylvania. I usually have a range broad of interests with lensing, non-Gaussian statistics, shear estimation, photometric redshift estimation, and baryonic feedback processes. But today's talk is going to be about a few cosmological results from the dark energy survey year-free data using non-Gaussian weak lensing statistics. So this is a weak lensing talk. I need to introduce a little bit of weak lensing. So we know that according to general relativity and with gravitational lensing, whenever we observe a distant galaxies, those photons will travel through space-time and their trajectories will appear distorted to the observer. And this is because we have some mass distribution in our universe that's deflecting those paths of lights. And the net effect is basically whenever you observe a galaxy image, that image will be slightly distorted compared to the original intrinsic galaxy shape. Now, those distortions are really tiny because we're in the weak gravitational lensing regime. But if we have a large enough sample of galaxies, that's great because we can still detect those distortions. And what's even better about it is that from those distortions, we have tools to infer the mass distributions that cause those distortions. And that's great because that mass is mostly dark matter that we wouldn't be able to observe otherwise. Now, what I just said is basically what we do when we talk about weak lensing mass map reconstruction. The main idea is that you have a sample of galaxy shapes, and per galaxy, you care about the ellipticity of a galaxy, which is basically 2 numbers per galaxy. And you can arrange those galaxy ellipticities into maps. These are simulated maps as a function of position in the sky. And we usually use galaxy ellipticity as a proxy of the shear field, which is the field that tells us, tells the galaxies how they need to be sheared by the mass distribution. And the shear field is related to the weak lensing gravitational potential, which is also related to the mass distribution. So using some tools, and the most famous one is the chi-squares algorithm, you can go from maps of your shear field to the map of the convergence field, the so-called weak lensing mass map, which has a very nice physical interpretation. This is mass distribution integrated along the line of sight. So it's projected mass distribution. And this is the same mass that caused those distortions in the galaxy ellipticities. This is again a simulated mass map or convergence mass map, convergence field. And basically the red spots in this map are overdense regions along the line of sight where you expect to find clusters, whereas underdense regions are the blue spots, so where you expect to find voids. Weak lensing mass maps are a very useful tool if you're interested in non-Gaussian statistics. If you look at the PDF of your convergence field, you realize it's non-Gaussian, and this long positive tail is a consequence of structure formation, and it's rich of cosmological information. And basically, normal cosmological analysis using photometric survey data mostly rely on Gaussian statistics like 2-point correlation functions to infer cosmology. But by doing so, they're missing all this information contained in this positive tail. Now, maps are great because they retain this information, and using some summary statistics, you can look at those. It's not necessary to have a map to do non-Gaussian statistics. Maybe just with a catalog of galaxy ellipticities, that's enough. You can compute the 3-point correlation function of those galaxy ellipticities. What I'm saying is that there is way more tools that can be applied to a map rather than to a catalog. Think about all the machine learning tools like convolutional neural network. Those are meant to be applied to a map rather than to a catalog. So that's what's great about maps. You have more tools. You can get more creative, I think. So in that year 3, we did a bunch of analysis using non-Gaussian statistics trying to infer cosmology. The first analysis which I led is the moments analysis, where I use second and third moments of the weak lensing mass maps. And the third moments are a proxy of the skewness of the field, so this long positive tail. The other analysis, one has been published by Dominic Zurcher, the other one for Niall Jeffrey is in the making. It'll be out in a few months. they look at the peaks of the weak lensing mass maps. So basically you choose a threshold and you count how many peaks in your map are above that threshold, and you can vary the threshold, of course. And this is highly non-Gaussian statistics, and we did cosmology with that as well. What's cool about non-Gaussian statistics? So as I mentioned before, they're probing additional information, which means that your cosmological constraints will be tighter compared to normal Gaussian statistics. But on top of that, observational systematics might affect Gaussian and non-Gaussian statistics differently. So if you're able to run analysis with both of these kind of statistics and they're both compatible, this should make you more comfortable about the robustness of and the reliability of your analysis. Okay, a few words about the dark energy survey. The dark energy survey is an imaging galaxy survey that has been observing 5,000 square degrees of the southern hemisphere. It's a photometric survey, so observing different bands, G, R, I, Z, and Y. And the final release, we're not there yet, will include shapes, photometric redshifts, and galaxy position for 300 million galaxies. We are not there yet. What we managed to publish so far and release to the public is half of the data set. So we have a shape catalog of 100 million galaxy. And we also have another galaxy sample for galaxy clustering that has 10 million galaxies. We use these two catalogs to make the so-called 3x2 point cosmological analysis, which we released last year, which combines 3 different 2-point correlation functions, so Gaussian statistics. This is our key result, and I'll be comparing the non-Gaussian statistics results to these results, because this is the benchmark for DS. Now let's go back to the non-Gaussian statistics stuff. Using these 100 galaxy shapes, we produced the DS year 3 weak lensing mass map. So this is real data right now. Again, red regions are overdense regions on the line of sight. Blue regions are underdense regions. And this is the biggest and largest weak lensing mass map ever created, just because we have, at the moment, we're lucky enough to have more galaxies than others. So, but this is very exciting, and that's what we use to do our R2 analysis. And this can be used for a number of different applications that also go beyond cosmology. Now, how do you go from the map to cosmological constraints? So this process is very similar for any cosmological analysis, but of course for non-Gaussian statistics, you have some subtle differences. So you start from a map. That's the map I just showed to you. And for instance, then you need to measure the statistic, a summary statistic in your map. In this case, these are turn moments, which again are a probe of the skewness of the map. And given a map, the skewness is just a number. Here you see multiple points because you want to smooth your map with different smoothing scales to highlight features at different scales. So that's why you have different points. After you have the measurement, you want to compare the measurement to model predictions, and this is done here in this third panel. These lines are different model predictions for the third moments as a function of the cosmological parameter S8. And through this comparison, you get your cosmological constraints. Now, what's the tricky part for non-Gaussian statistics? Well, the tricky part is getting model predictions right, and this is really hard for Gaussian statistics. It's even harder for non-Gaussian ones. And usually you have two potential approaches. From one hand, you can try to model analytically your observable. And the problem is that this is really hard to do. And in most of the cases, we have no idea how to do it. But if you manage to do it, then it's great because it's not too computationally expensive to get model predictions, at least compared to the other approach, which is this one in the bottom right, which consists of for modeling your observable. So you basically run many n-body simulations for different values of your cosmological parameters. And for each of those, you make sure that you faithfully reproduce your weak lensing observable. So you need to be able to reproduce the right redshift distribution, the right shape noise, and the right mask of your weak lensing sample. And then you measure in simulations the same non-Gaussian statistics that you'll be measuring in data. And then you do the comparison. That's great because this can be applied to any non-Gaussian statistics, but it's very computationally expensive because you need to run a lot of simulations and you need to make sure that your simulations have everything that is in the data, which is also not straightforward. So the first approach, that's what I used in my moments analysis. The second approach, that what has been used in this peaks analysis from DS. A few more words about the first approach, because this is what I used and developed. Basically, my model predictions are based on perturbation theory. This is the analytical expression for the third moment of the matter. Then you can put in some lensing kernel and integrate along the line of sight, and you get the third moments or the skewness of your lensing mass map. These are valid only until certain scales. You can go to too much smaller scales with this approach. And usually there is an extension. You can extend these analytical predictions to small scales. Here in the bottom, here you have a few coefficients, A1, A2, B1, B2, and C1, C2. And those are fitted against some suite of n-body simulations and allows you basically to extend this formalism to very small scales. And this is basically what I use for my analysis, for my moments analysis. Of course, all of this has been gone through some serious validation. For instance, once I developed my analytical model for the third moments, I went to 2 different sets of independent n-body simulations, and I measured the moments in those simulations, and I compared to my model predictions, and the comparison was good enough. So you can see here this on the left. This is basically a ratio -1. So if it's on 0, that's great. And this is the ratio between my model predictions and simulations in red. And you can see is on top of 0 within uncertainty, which is great. And the actual DS free uncertainty are in gray, are much bigger, which means we can safely use this for our analysis with no problem. The cosmological analysis using non-Gaussian statistics is as complex as the fiducial 3x2 point analysis from DS. We're varying 5 cosmological parameters. We're including astrophysical effects like intrinsic alignment, and we're also including all the calibration systematics. So we're doing something more complex, but we're not simplifying or making some simplifying assumptions in terms of complexity. We really want this analysis to be as robust as the fiducial Gaussian analysis from DS. And on top of that, we also need to check some extra systematics specific to these non-Gaussian statistics. For instance, here on the right, I'm looking at the effect of PSF systematics on second and third moments. Second moments are Gaussian statistics, third moments are non-Gaussian. And the funny thing we found out is that actually PSF systematics, so PSF residuals, they have a very small skewness. They're not very skewed. So the third moments is almost negligible here. And you cannot even see it's right on top of 0, basically. And this goes back to what I said at the beginning of my talk, that for some systematics, they might affect Gaussian and non-Gaussian statistics differently, and they might be less or more important for your observable. That's all new stuff. That's something we found out and we didn't expect in our data. Okay, once we made sure that the modeling is right and everything is under control, these are the cosmological results from the moments analysis. So as I said before, I actually combined second moments and third moments. Second moments is the analogous of Gaussian statistics as a cosmic shear. Third moments is the non-Gaussian part of it. And here you can see the posterior for sigma 8, omega mater, and S8. In red, constraints from second moments. In blue from third moments, and in black, the combination of the two. So you can see third moments are less constraining because it's a noisier statistic, but they probe a slightly different region of the parameter space. And we checked that red and blue are statistically compatible with each other, even though they look a little bit separated. That's a statistical fluke. It's completely okay. And this is great because it means, they're so different. They're probing different information. So the fact they are consistent with each other makes us more confident about the robustness of this analysis. And when you combine those, you get the black contours, which is tighter of 30% over second moments. And this is because third moments break the sigma 8 omega matter degeneracy and they bring in additional information. And the constraints we get out of this analysis are actually the most stringent constraints from a weak lensing analysis to date, which is pretty remarkable. And this is again due to the fact we are adding more information. These are the results from the other non-Gaussian analysis that we run with the SCR3 data. This is from Dominic Zurcher. It's peaks, and also in their case, they're combining with the power spectra. Results are qualitatively and quantitatively very similar to the moments analysis. Once you add the peaks, you improve constraints, and the numbers here, the constraining power is very similar to the moments analysis ones. And but what I want to say is that this is a completely different pipeline. Moments is analytical predictions. This is based on n-body simulations. So very different pipelines, very different approaches, but very similar results. Of course, we run a number of very large systematic tests, varying our analysis choices, removing redshift bins, small scales versus large scales, and everything looked very robust, which is great. These are consistency tests with other DS probes. Here on the left, you can see the constraints on S8 from the moments analysis in gray, from the peaks analysis in green, a cosmic shear in red, and 3x2 point in yellow. And well, first of all, it's great. Everything is pretty consistent. Again, completely different pipelines, moments and peaks, different pipelines, and there are also different pipelines compared to cosmic shear and 3x2 point. But yeah, the cool thing is that the moments analysis is more constraining the cosmic shear because this has additional non-Gaussian information, and it is as constraining as this 3x2 point analysis, despite the fact the 3x2 point analysis also include galaxy clustering, whereas moments analysis is with cleansing only. And this is again because we're bringing in additional non-Gaussian information. So imagine how tight it could be if we were able to do non-Gaussian analysis of galaxy clustering also. That's something we're thinking of. Last thing on the right, this is consistency with Planck. And when you look at the moments and check on consistency with Planck, it's a 2.2, 2.8 sigma tension. Third moments, interestingly, alone, they show a 2.8 sigma tension. This is what it is, but I think in the future, non-Gaussian statistics can tell something more about, tension with Planck in an independent way. Just finish off saying that for the future, we're planning to do more of this and apply this to SCR6 data, and also to include more different types of non-Gaussian statistics.